Welcome to the Explainer. Today, we're unpacking the CIA Triad in cybersecurity, complete with real-world examples. Look, if you're building software, writing code, or architecting systems, you are in the business of security whether you realize it or not. We're looking at the absolute gold standard here, the ultimate mental model for security. It's not just theory, it's the lens through which literally every major security decision gets made. Okay, let's dive into this.
Here's our roadmap for today. First, we'll cover the core of cybersecurity. Then we'll hit confidentiality, integrity, and availability. After that, we're going to balance the triad. And finally, put your knowledge to the test. Let's get moving.
Section 1, the core of cybersecurity. You know, a lot of developers hear about security frameworks and just kind of roll their eyes, right? They think it's just academic theory for auditors. But actually, scratch that, it's totally not. Every single security requirement you're going to face maps directly to this framework. It shifts security from an abstract concept into a practical, everyday tool. The CIA Triad, confidentiality, integrity, and availability, is your foundational model. Think of it like this interlocking Venn diagram. Every single security control you put into your code has to strengthen one or more of these pillars. It gives you a way to ask the right questions during system design. Who should see this data? Who can modify it? And hey, is it actually going to be there when they need it? As we go through these, I really want you to apply this directly to the code you're writing right now.
Section 2, confidentiality, protecting data privacy. Now, what's really interesting about this slide is that it sets up the core focus for our very first pillar. This is usually what pops into people's heads first when they hear cybersecurity. The formal definition, ensuring that information is accessible only to those authorized to access it. Basically, we're anchoring on one very direct question: who should be able to see this data? But honestly, it goes way deeper than just reading a database row. In many systems, just knowing that certain data exists is a massive confidentiality violation. I mean, think about a celebrity checking into a specific rehab clinic. Just the mere existence of that record, highly, highly sensitive. So how do you, as a developer, actually implement this in the real world? Well, there are 5 crucial implementation layers you've got to use to defend your data. First up, encryption at rest, using algorithms like AES for stored data. Second, encryption in transit, using TLS to protect data moving across the wire. Third, access controls, and that means both authentication to verify identity and authorization to verify permissions. Fourth, data classification, labeling data by its sensitivity so you apply the right protections. And fifth, secrets management. Listen to me. Never, ever hard code your API keys or database passwords in your source code. Each of these layers is absolutely vital. Just let that number sink in for a second. 147 million. That's how many customer records were exposed in the 2017 Equifax breach. I mean, talk about the data-driven shock value of what happens when confidentiality fails on a massive scale. To put that into perspective, that's nearly half the US population having their most sensitive financial data exposed to completely unauthorized parties. And here's the really harsh reality. That Equifax breach, along with the 2019 Capital One breach that exposed another 106 million records, they were entirely preventable. Capital One failed because of a misconfigured web application firewall. Equifax failed because of an unpatched Apache Struts vulnerability that literally had a fix available for months. Like, no way. These weren't zero-day, unpreventable acts of nature executed by super hackers in hoodies. They were configuration and maintenance failures by developers and operations teams. This really cements the real-world liability you carry every single time you write and deploy code.
Section 3, integrity, ensuring data trust.
So, while integrity failures might be a bit subtler and, less headline-grabbing than confidentiality breaches, they are just as damaging. Integrity means ensuring that information is accurate, complete, and hasn't been tampered with. We want to anchor this pillar to a direct question. Can I trust that this data hasn't been changed by someone who shouldn't have? And this applies everywhere, to data sitting in your database, data moving across a network, and data actively being processed right there in your application logic. Developers have specific tools for this too. Input validation to reject malformed data. Hashing like SHA-256 to detect changes. Digital signatures to verify authenticity. Database constraints to enforce your data rules. And audit trails to log exactly who changed what and when. So, the crucial point is, these are not optional niceties. Building these in is literally the difference between catching a data tampering incident immediately and being completely blind to it while your system rots from the inside out. To illustrate real-world integrity failures, just think about these stealthy attacks. An attacker doesn't always want to steal your data, right? Sometimes they'll use a SQL injection to just change a price to zero, or they use a man-in-the-middle attack to alter a bank transfer destination account number while it's in transit. Or hey, maybe your API just carelessly accepts a negative quantity in a shopping cart, and suddenly your entire inventory database is utterly corrupted. These are pure failures of the developer's craft to protect data integrity. Section 4. Availability, keeping systems online. Now, unlike the stealthy nature of those first two pillars, attacks on availability are meant to be loud, obvious, and highly disruptive. Availability is all about ensuring that systems and data are accessible to authorized users when they actually need them. The anchoring question here is simply, is it there when authorized users need it? And keep in mind, a system that is technically online but takes 30 seconds to load a page, yeah, that isn't truly available. Performance and usability under load are absolutely key parts of this pillar. So, how do we actually build for availability? It's all through strategies like redundancy across multiple servers, load balancing to handle those massive traffic spikes, rate limiting to stop a single rogue bot from overwhelming you, graceful degradation so a failing component doesn't crash the whole shebang, and of course, proactive monitoring. Ultimately, good availability engineering is just good software engineering. It requires us developers to constantly prepare for both massive traffic spikes and the inevitable component failures. And when availability fails, it can be absolutely devastating. In 2021, a single configuration change at Fastly, which is a major content delivery network, triggered a massive internet chain reaction. It took down huge portions of the web for about an hour. We're talking Amazon, Reddit, and even the UK government's website went dark. It just goes to show how one availability failure in a critical dependency can have a globally disruptive ripple effect. Section 5, Balancing the CIA Triad. Let's move to and see how this builds, because there is an inherent tension between these three pillars we really need to talk about. Because there is this inherent tension between the three pillars, you always have to make trade-offs. For example, a banking app absolutely must prioritize integrity above all else. If their system is under heavy load, it is way better for a transaction to fail or just be slow, which hurts availability, than for a transaction to process incorrectly and put money in the wrong account. A wrong balance in banking is catastrophic. On the flip side, look at a social media platform. They prioritize availability. If a few likes or comments drop out, a minor integrity issue, it's an acceptable trade-off to keep the site online and loading instantly for millions of users. You've got to balance the triad based on your specific context. Section 6. Test your CIA knowledge. Let's do this. All right, it's time to lock in the frameworks you've just learned with a quick interactive check. I'll read the scenario. You tell me the pillar. Scenario 1. A company discovers that an attacker has been reading internal documents without authorization. Which CIA pillar has been violated? Take a second. Lock in your answer mentally. Got it? The answer is confidentiality. The logic here is super straightforward. Unauthorized reading or viewing of data is a confidentiality breach. If the attacker had modified those documents while they were in there, well, that would be an integrity breach. And if they had deleted them entirely just to cause disruption, yep, that would be an availability breach. Let's try scenario 2. Think back to the developer tools we discussed earlier. Which developer practice primarily protects data integrity? The answer is input validation. By ensuring only correct, properly formatted data enters your system, you protect its integrity. Just as a quick refresher on the other tools we covered, TLS and encryption handle confidentiality, while load balancing and redundancy handle availability. I'll leave you with this final provocative thought. You can't maximize all three perfectly. And honestly, you shouldn't even try. Trade-offs are inevitable. Perfect security? It's a total myth. The true hallmark of a great engineer is making conscious, informed trade-offs rather than accidental ones. So look at the last pull request you submitted. Did you accidentally sacrifice the integrity of your system just to keep it online, or did you make a deliberate choice? Think about it. Thanks for joining this explainer, and keep building securely.